Now we'll start the section of this afternoon. The speaker is Maísa Magalhães from ENCE, IBGE, and the title of the presentation is Adaptive Control Chart for Linear Profile Monitoring.
Good afternoon. I would like to thank Linda for the invitation. So, this work is more academic work. I'm going to talk about adaptive control chart for linear profile monitoring. It's a joint work with Viviane and Francisco. Aqui, Linda, okay. So, our objective here is to investigate the monitoring of a process when its quality characteristic is represented by a linear profile. So we propose the control chart with variable sample size and variable sample interval. Linda, tem que voltar. Eu não sei porque que está andando. Okay. For monitoring a quality characteristic described by a linear profile. Okay. So the performance of the proposed VSSI control chart is compared to the fixed parameter control chart that was proposed by Kang-Albin for the monitoring of linear profiles, and also we compared the proposed chart with the variable sample size and variable sample interval. The performance measured, we obtain the adjusted average time to signal. Also, we consider shifts of different magnitudes in the process parameters. Okay. So, let me say which is a profile. Profile is a functional relationship between a response variable and one or more explanatory variables. Profile monitors is used to check the stability of this relationship over time. So there are production processes whose nature leads to the need of using a function profile to monitor its quality. The profile has to be monitored to check if it remains unaltered, that is, the process remains in control, if it has changed too much. The production process is out of control. It demands corrective actions. So, the example. Here you have a linear profile, non-linear profile in control. The target value is the black line, or the curve. Here you have a linear profile and a non-linear profile out of control. So the monitoring of linear profile consists of keeping track of the regression coefficients beta 0 and beta 1 of the profile, which can be done, for example, for fixed parameter control charts, what Kang-Albin use a chi-square chart when the coefficients were obtained by least square, and also we have a paper that we use also the fixed parameter control charts to monitor a linear profile, that we obtain the coefficients parameters by Kalman filter. Now we are proposing a variable design parameter control chart. Also, we are going to obtain the coefficients by least square, ordinary least square. So the work of Kang-Albin, they propose FP, chi-square control chart, to monitor a linear profile represented by a linear regression model. They monitor the coefficients parameters by chi-square control chart. The sample size, all the design parameters is kept fixed. Okay. So this example of the Kang-Albin chart. This is the statistic that is plotted. And they have just a region on the chart. Okay. So our proposed chart, you have a control limit, a warning limit, two different sample size, a small sample size, and a large sample size, and N2, N1 is a small one, and two different sampling intervals, the long sampling interval and the short sampling interval. So the methodology of the chart is, if the sample statistic falls between the warning region here, the action region here, you obtain parameters with small sample size and a long sample interval. If the plotted statistics falls in the warning region, you are going to get a big sample size and a short sample interval. In the statistics that is plotted is going to depend on the sample size. So then, what I said is the position of the last sample point on the chart establishes the size of the next sample in the sample interval. So if the statistics before the last statistic falls in the warning region, the next subgroup sample size is going to have N1 and H1 parameters. If they fall in the warning region, the next subgroup sample size is going to be N2 in H2. Okay. So the linear profile beam monitoring is a simple linear regression model. This is the I represents the sample statistic, J the sample size, the process parameters being monitored is the beta 0 and beta 1. The parameters that design process is given this way. Okay, and I assume that they are known. So we are just considering phase 2. So processing control, you have these parameters. Okay, process alpha of control, they're going to have a shift in the coefficients parameters. So, as I said, the parameter is going to be estimated by ordinary least square. The following statistics computed and plotted in control chart. When the process is in control, the Q-square has a distribution, a Q-square distribution with 2 degrees of freedom, and control limit is given by this way. And alpha is the probability of type error 1. It's given by that expression here. Huh? Okay. When the process begins, the sample size of the first sample is chosen at random. They can be with size N1 or N2. When the process is out of control, if occurs a shift in the parameters, so the chi-square has a non-central chi-square distribution with non-centrality parameter given by this way here. Then, from the observations, the aim is to verify if the process remains under control, that is, if the parameters have not changed. Changes or deviations from the parameter vector are analyzed. So we have to obtain the performance measured, the adjusted average time to signal. So how we are going to get this? By a Markov chain, considering 5 states. State 1, if the statistics falls in the warning region, central region, and the process is in control. State 2, if the statistic that's going to be plotted is in the warning region, and the process is in control. And also state 3, if the plotted statistic falls in the central region, and the process is out of control. And the state 4 is the plotted statistic falls in the warning region, and the process is out of control. State 5 is the absorbing state. So to get the adjust the average time to signal, you consider the average time of cycle, that is the time that process stays in control, plus the average time to signal. With this, you have the average time to signal, and you take the expected value, so you get the adjusted average time to signal. And we are considering that the time the process stays in control has an exponential distribution. So now this is the expression of the adjusted average time to signal. It's given that way. Okay, I'm going to say how the transition probabilities represents. Just as an example, P1, 2. So it's the probability that the last point was in the warning region. It goes to the central region. It goes to the warning region with parameters N1 and H1. For P2, P21 is the probability that the parameters felt the last one, the statistical x chi square 1 I minus 1 felt in the warning region. It went to the central region with parameters N2 and H2. And also considers its process stays in control. It's given by the probability T is greater than H1, in probability that T is greater than H2. Okay. Now, this is a simple, the percentage gain that I'm going to calculate. Okay, percentage gain of the probe chart compared to the fixed parameter control chart. Also, to get the design parameters for the comparison to be fair, the same amount of resources effort spent with inspections and and false alarms when the process is in control should be imposed. So we have to made this restriction here. When this is the fixed parameter control for the fixed parameter control chart, this is also for the fixed parameter control chart. In the average, they have the same. They have to spend the same amount of effort, so inspections. É esse? Isso. Não sei como é que para isso. Não, é outro. É esse aqui. So comparison between the two control charts, considering the Kangen-Albin example. So we propose a chart. We'd like to compare that chart with the Kangen-Albin chart. So Kangen-Albin considering statistical process control of semiconductors, manufacturing and monitoring a linear profile. The measured pressure in the etch chamber, Y, is monitoring through a mass flow controller that allows the max flux X in the chamber. The model in the article of Kangen-Albin was they have the parameters beta 0 is equal to 3 and beta 1 is equal to 2. Considering that, okay, this is when the process is out of control and when the process is in control. Okay. So pressure Y is a linear function of the mass flux. Here is when the process is in control. We are considering that assumptions. And here when the process is out of control. There is a shift in beta 0 and beta 1. Okay. So considering the Kangen-Albin example, delta 0 varies between 0.2 and 2 with steps of size 0.2. Delta 1 varies between 0.025 to 0.25 with steps of 0.025. So here you just put some examples. This is with the fixed parameter control chart. everything is fixed. Here, just the interval is varying. This is VSS, that is variable sample size. This is the chart that we are proposing. So, considering shifts only in the intercept first. So here we have all the comparisons with FP, VSI, VSS, VSSI, and best performance. Looking at here in the AATS in the standard deviation is, of course, FVSS, that way. The percentage gain of the adaptive chi-square charts compared to FP chart considered shifts only in the intercept beta 0. So, aperta mais uma vez aí. Dá mais uma apertada. Ah, tá. The best performance of all adaptive charts is for shifts between 0.6 and 1.2 here, where it's all red. Okay. Now consider just shifts in the slope. Here again, you have the way, the best one is the VSS, VSS, VSI, and FFP. Here you have the adjusted average time to signal, here the standard deviation. Now consider the percent gain in the AATS for the proposed charts for the shifts in the slope. Now the best performance is VSS after VSSI and for shifts between 0.075 and this one here. No. Até aqui, mais ou menos. Until here, it was in red. Okay. You did a sensitive analysis just for the variable sample size. A sensitive analysis was considered to verify how. Now, when we are talking about just the variable sample size. So we can talk about the average run length. So to verify how the average run length changes when the parameters beta 0, beta 1, and sigma are perturbed. The scenario 1, you consider that values here. In scenario 2, you consider that values here. For both scenarios, we consider the following: 9 combinations of N0 and N1, N2 taking values between N1 plus 1 and 30. The ARL was calculated for each combination in each scenario. The results obtained were similar qualitatively. Select combination, so because the results were similar, you select some combination to show here. So, for the shifts 0.6 and for beta 0 and beta 1, in beta 0, 0.8 and beta 1, the RL is almost the same qualitatively. Here. In second scenario, volta lá. Yes. We have gamma, we have shifts in sigma, and this is the table I'm going to talk about next. Yes. No, for the large shifts in gamma, the RL is lowest. So, conclusions. A better performance of the proposed charts for monitoring linear profile was observed when compared to FP chi-square chart. However, it's important that comparison with other control charts to monitor linear profiles be made. Also, it's important to considered a large range of design parameters, a sensitivity analysis for the VSI and VSSI charts. Also, you have to do it. Indeed, we have already done. We are finished the results for the VP chart and also a more complete analysis for VSSI, VSSI, VSSI and VSSI charts. Falei muito rápido, né?
Hello.
Is it possible for you to give an example of a production that could be used? I mean, the Albin example, Kangen-Albin, my mind goes to, whenever I see profiles, my mind goes to batch processes, right? Mm-hmm. In batch processes, from this batch to another batch, you have profiles of temperature, pressure, pH, whatever you might have. This is more like, as far as I can see, the parts production, like a discrete production, rather than a...
The adaptive control charts,
yeah.
I don't have an example because I just have an example for the Kangen-Albin example, that is that for pressure, the max flow controller.
Okay. So what would each profile correspond to? Then, I mean, is it a one shot of the manufacturing, or the manufacturing is going on?
I understand.
It is my limited view. I'm not. It's not a question. It's I can understand it in batch processes, because for one batch you have a profile. I can understand it, but but I am having hard time in regular production, discrete production, parts manufacturing. What would that correspond to? I mean, if you have an example, just for me to understand better.
I have an example, like if you think about the X-bar chart, the X-bar chart, you have a quality characteristic that not represent, let's say, let's say X equal to me plus epsilon. So you have one that is represented by Y, something else that beta 0, but beta 1, X plus Y. I understand that the same way. Mm-hmm. The process that Kangen-Albin gave, the example was the same. Instead of use a model that is represented by X plus me plus epsilon, is not represented by that way. Is represented by Y beta 0 plus beta 1 X plus, it's like this, not like batch. She didn't talk about batch. And is that
okay? So it's not a constant process, but the constant process that we assume in a Schuhart chart, classic Schuhart chart. It's not that you're saying it's a linear, like in time,
it's
or
not
whatever.
like the relationship, the quality characteristic. You cannot represent like just a mean plus something. Yeah. You have to represent some a function plus a real row.
Okay, thank you.
It's also my doubt. So I understand we shouldn't compare your proposed chart with the standard chart.
No.
No, it's not.
No.
Okay.
Too late?
No.
Thank you very much.
It's too late. More questions?
This model.
Let me... You are so far from me.
Okay. This model, when that showed you in the beginning, when talk about the subgroups, okay? There is limit number or standard subgroups at the parameter.
No, in my data work here, no. In fact, you use N. You didn't take, you take not, you don't, sorry. You didn't take n subgroups of size 5. It was not like Shihart chart. Is that what you're asking?
Okay.
Go ahead.
Let's go on 5.
No,
No,
it's not that.
no.
Because in fact, you are very, how can I say, constrained. The model is not constrained to the model of the Kangen-Alben, because you develop the model. Okay. But to apply to get the results, you are in some way constrained to the example of Kangen-Alben, because we would like to compare with we propose with the model of Kangen-Alben. So we got very restrict to the model of Kangen-Alben, because she gave some numbers. She gave the numbers of beta 0, beta 1, and the X, the numbers of the subgroups.
Okay.
Also, and N0 was the observation was taken. I believe, I don't remember, it was 5 or something like that. So you vary our subgroups according to her subgroups.
Okay. That's okay.
To compare.
Okay. Thank you.
Give us some examples of application of your proposed chart, since this is linking the university with the industry. What would be the industrial applications of, other than calibration?
I don't know. I say that there is an example, but I'm not able to describe to you the whole example. I say that there is an article, just one article, that uses the profiles that you can represent a quality characteristic by a profile that using madeira, corta madeira. Como é que fala corta madeira? Wood. Cut wood in something that you cut a wood that the diameter has can model the diameter by a profile. Is the Staudhammer, the author is a woman. I have just that example and the Kangen-Alben example. But also, all of them don't use variable parameter control charts. They use fixed parameter control charts with the same N, a same H, a same N and H, and the control limits. They don't vary the control limits. I just have these 2 examples. Okay.
I think I have another example. I have another example. It's related price of some stock and by the market stock. And at every market stock, you get some sample, like a week of the prices, and you relate the price of some stock with the market stock. So you would like to know if the coefficient linear or the angular, you have changed by the time, for example. So this is another application of this.
But is a linear profile?
Yes. Okay.
Mm-hmm.
So more questions? So thank you, Maísa, for your presentation. Now the second presentation is Guilherme Moraes Ferraudo from Monsanto, and the title of his presentation is Demands, Paradigms of Analysis in the Agricultural Market.
Posso abrir direto? Depois eu ponho.
Você não consegue manter isso praticamente.
Hello. Good afternoon, everyone. Here I present not some formulas and not some some statistical model, just 3 problems we are facing inside Monsanto. And just to clarify, I'm working in technology development. We are the bridge between plant breeding, our research team, and the market and the economics team. So we have to bring analysis to add value to the grower. Okay. My team's data management team. Since 2010, we are building our team with data capacity, or we have geography, we have geospatial analysis, we have statisticians, me and Lucimara, and we have 3 interns to help us to get the data from the database and deliver the results from the technical managers. Okay, please. The outline here, first issue is the multivariate quality statistical control. Another one is the agronomic system trials, design of experiments in a big data perspective. Okay. The current scenario. We run the quality control charts for each random variable that we gather in the field. The field observations that we analyze are harvest population, 1,000 plants per hectare, moisture of grain, total of damaged plants, with the stalk loading or root loading, and yield in quintals per hectare. We know that that exists the correlation among these field observations. The statisticians call random variables. The agronomists call trait. Okay, just to explain about the difference between the names. Next one. So here we are analyzing in the practice. You know. This chart here is the average from the whole experiments. Its dot here is the one plot in the field for this hybrid. This one's for another hybrid. So we evaluate all the experiment. Or if you desire, you can analyze each field trial. So we are analyzing yield, also moisture, harvest population, and so on. So because the correlation exists, we are discussing how can we evaluate all these traits together and bring it and make the analysis more efficiently. So that's what I'm trying to put here. Next one, just the moisture here. The moisture. Okay.
Is there a difference between squares and circles in your plot?
Oh, the replications. Sorry, we have 2 replications in field trial. We have a 20 field trial across Brazil, and since Rio Grande do Sul to Mato Grosso or Bahia and the east. So each point is a replication in a plot.
Okay, but the circle means something and the square means another thing?
The circle is the one replication, and the square is the other replication in the same field. Okay, sorry.
If you plot it this way, do we lose the time? Is there a time component or a space component?
Here, hybrids. Each hybrids that we are evaluating to make a launch, commercial launch.
Okay, so what is the difference between these points? I'm confused.
Here you have the field observations.
So these are like experiments at different fields?
Here, inside the hybrids. Yeah.
Exactly. Okay, so that's the space component, not time.
No, it's space component.
Classic control chart will have usually the time.
Okay.
So you have the space component. Okay.
Yeah, it's the space component. So the question that we are trying to understand, does the Hotelling control chart the best scenario? I don't know. How can we implement that in the components analysis, né? And how does it can add value to our pipeline analysis? So just one example we are sharing with you. And we can talk about this specific problem. Another one, the second one, we are since 2008, the Monsanto has the agronomic system trials. So what is the agronomic system trials? We are trying to understand the system that happens inside the grower. So we are consider the herbicide rotation, the molecular, the chemical. We are trying to understand what's the best crop rotation, soybean wheat, or soybean fallow. Soybean fallow is no crop. So just to explain here, treatment 1, no herbicide rotation. In year 1, we plant soybean and wheat. After, soybean wheat and soybean wheat. So at the end of the third year, what's the value that the grower can capture with the system? And we are trying to understand how many applications with different herbicides, what's the resistance about the weeds and some diseases. So not the yield is our concern here. It's about the sustainability of the agronomic system for the grower. Here is more related to the commercial value to the grower. It's not the research perspective. Okay. So across Brazil, we have different systems. With we have here the same rotation, crop rotation, but we made the herbicide rotation. Here, another crop rotation. Okay. So next slide, please. Here, for instance, we can compare the presence or absence of herbicide rotations in ag system. Okay, so we keep the crop rotation, compare the herbicide rotation here. The next one, we can compare fallow versus wheat, because I don't know, Monsanto defends the direct planting, né? With the where you can plant, for example, soybean, wheat, soybean, and we do not recommend the fallow for the agronomic system for the grower. It's okay. So here we can compare. The wheat is the winter crop with the fallow. And what's the again? Fallow é pousio. Fica sem cultura. Eu fico solo exposto. Exposed soil. Okay. And so what can use to analyze it besides ANOVA with contrast? So if you go back, please. One more. Here we just make the contrast between different treatments, but we know that each treatment is planted at the same field. So, for example, this treatment, we have 4 or 5 years of data at the same field. So we know that the correlation exists, and how can we model this correlation? Okay, next, please. So what's the adequate model to accommodate the correlation structure due to the crops planting at the same field across years? So it's our first concern here. Second one, how can we analyze the year effect as a result from crops and herbicides rotation? Here we have a confound effect. We don't know how to model it. And also agronomic practices, because at the same region, for example, Paraná, we know that the neighborhood farmers don't have the same agronomic practices. Okay, so it's a effect that we should consider here. How can we implement that in the company, and how does it can add value to our pipeline analysis? Another experience that I will share with you. Growers and decision makers must be convinced about that, not me as a statistician. How can we convince the grower? He can see that's the bring value for him. Okay, that is the challenge for us, because here is the forum with specialized people, but when we go to the field, the talk is a little bit different. Okay. And here we are not facing yet, but we are discussing, because we are trying to understand what is the data needs in the future. Several teams are generating data consistently in Monsanto. Every field research has an iPad, and every time we are getting the data. So what is the impact of DOE in a big data, since the structure defined by DOE will be lost when the data is put together? Here I'm talking about the 30 millions of data. What's the impact of DOE in this big data perspective? So here I put extreme conditions, extreme scenarios, but I would like to share with this forum here. If we do not plan the experiment and yet run the collection data in the same way, what would be the impact of this non-design experiment in the big data analysis? Here we know that the asymptotic theory, I think is not so important. If I have 30 million, maybe the significant of its effect, statistical significance of its effect is achieved with a huge amount of data. So that's the question that we are discussing right now in Monsanto, but is not happening right now in Monsanto. So Linda, it's that. Thanks for your time, and I'm open for the question.
Could you expand a little bit on how you would use big data relating to your field?
My field? Yeah, the first team that used the big data in Monsanto is the genomics and proteomics team that started the big data some years ago. In my case, we are getting the data from yield trials since 2001, from 2014, for example, for corn. And besides corn, we have this same database for cotton, soybean, and herbicides perspective. So we are trying to understand what's the best, for example, planting date, considering the difference between regions in Brazil. Another thing, pricing. Price is important to use the
data could help that.
Yeah.
Really? Well, I don't understand much about your field of knowledge, but
big data help because since 2013 that I began to interpret this big data, we are challenging our 25 years working for Monsanto, and today we are looking at the big data and planning a new experiment, planning something that have a blind spot, for example, for technical managers. So the big data is challenging our concepts inside the company.
It's clearer now. Thank you.
Okay, are we switching? Sorry. Okay, we switch the...
Okay.
I don't know whether there's a difference that speakers should have the better one, I suppose. The last part, it's an interesting thing we were talking about this morning as well. The big data and designing experiments. I say this all the time about big data because now we're facing with big data a lot in our applications as well. Each company comes to us with a lot of data and they say, do something with it. Then they don't know what we're going to do with it. But the problem is this. In the big data, all the methods in big data, what you usually get is the correlations. Like this variable and this variable are correlated, let's say positively correlated. But that doesn't mean that if I increase that one of them, the increase, causality. So there's a difference between correlation and causality. With observational data, you often get correlation. That was the power of the controlled experiments. Then you control everything else. You specifically change certain things so that you can figure out the causality, right? So we were discussing that how can we do systematic data collection in a big data environment? Because our 2 to the 3s, I mean, it's like 16 run experiments, 12, 40 run, it doesn't mean much when you have 30 million data points.